Hello and welcome to Code Skwela. We are now in our hour number 6 of this Harvard CS50 Computer Science course. And just a quick recap of what we have learned from the previous hour, which is hour number 5. So yeah, from that hour of lecture, it has started uh, discussing with arrays, although it has not yet been discussed in detail. And so another thing to point out also is the word compiling or the process of compiling. So with compiling, there are four steps that we have to remember. So the first one is pre-processing, which is finding and replacing the includes or references to other files. And then next would be compiling, which is turning your source code into assembly language. Next would be assembling, or the third step is turning the assembly language into the actual zeros and ones or in binary code. And then after that is the linking, which is combining all of the binary codes that from your different generated uh, source files, okay, or source codes, okay. And so another thing also is ways of debugging. With VS Code, you can debug using debug 50 command, and then there's also a mention of rubber duck debugging technique. So okay, so wherein you pretend you are talking to a duck to explain and polish out your logic or the issues that you are or errors that you are encountering while you're coding, okay. And then a short mention of data types. And so uh, continuing this one on lecture hour number 6 is I guess would be a continuation of the data types that has been discussed from the previous hour. And so let us not make this any further. By the way, don't forget to like and subscribe to our channel so that you get updated to our future videos and also our uh, uh, any new tutorials that would come out. Okay, so yeah, join me today in this another hour of lecture for the Harvard CS50, and let's keep on learning and let's start. Okay.
Floating point imprecision per last week aside, but let's consider the design of this program. Like, what is kind of bad about it? Or if we maintain this program longer term, are we going to regret the design of this program? What might not be ideal
Yeah, if you
here?
can recall, he was making a program of doing averages or calculating an average of the three scores.
Yeah, so in this case, I have hard-coded my 3 scores. So if I'm hearing you correctly, this program is only ever going to tell me this specific average. I'm not even using something like getInt or getFloat to get 3 different scores. So that's not good. And suppose that we wait later in the semester, I think other problems could arise. Yeah.
You have to rewrite again since you're hard coding the values that
I
you
can't
are
reuse the
calculating.
number because I
Yeah.
haven't stored the average in some variable, which in this program, not a big deal, but certainly if I wanted to reuse it elsewhere, that's a problem. And let's fast forward again a little later in the semester. I don't just have 3 test scores or exam scores. Maybe I have 4 or 5 or 6. Where might this take us? Yeah, I've sort of capped this program at 3. And honestly, this is just kind of bordering on copy-paste. Even though the variables, yes, have different names, score 1, score 2, score 3. Imagine doing this for like a whole grade book for a class, having score 4, 5, 6, 11, 10, 12,
So
20,
with this
30.
kind of code,
like,
it's
that's a
very
lot of
rigid,
variables. And you can
okay?
imagine just how ugly the code
There's not much
starts to get if you're just defining
flexibility
variable
with
after
this one.
variable after variable. So it turns out there are better ways in languages like C if you actually want to have multiple values stored in memory that happen to be of the same data type. And so
Now
let's take a
comes
look back
in
at this
with
memory
the
here to see
arrays.
what these things might
Yeah.
look like in memory. Here's that grid of memory. And each of these, recall, represents a byte. So just to be clear, if I store score 1 in memory first, how many bytes will it take up? So 4, aka 32 bits. So I might draw score 1 as filling up this part of the memory. It's really up to the computer as to whether it goes here or down there or wherever. I'm just keeping the pictures clean, though, for today, from the top left on down. If I then declare another variable called score 2, it might end up over there, also taking up 4 bytes. And then score 3 might end up here. And so that's just representing what's going on inside of the computer's memory. But technically speaking, to be clear, per week 0, what's really being stored in the computer's memory are patterns of zeros and ones. 32 total in this case, because 32 bits is 4 bytes. But again, it sort of gets boring quickly to think in and look at binary all the time. So we'll generally abstract this away as just using decimal numbers in this case instead. But there might be a better way to store not just 3 of these things, but maybe 4, maybe 5, maybe 10, maybe more, by declaring one variable to store all of them instead of 3 or 4 or 5 or more individual variables. And the way to do this is by way of something generally known as an array. An array is another type of data that allows you to store multiple values of the same type back to back to back. That is to say, contiguously. So an array can let you create memory for 1 int, or 2, or 3, or even more than that, but describe them all using the same variable name, the same one name. So for instance, if for one program I only need 3 integers, but I don't want to sort of messily declare them as score 1, score 2, score 3, I can actually do this instead. And this is today's first new piece of syntax, the square brackets that we're now seeing. This line of code here is similar to int score 1 semicolon, or int score 1 equals 72 semicolon. This line of code is declaring for me, so to speak, an array of size 3. And that array is going to store 3 integers. Why? Because the type of that array is an int here.
So
the
you
square
can think
brackets
of
tell
it
the computer
as,
how many ints you want, in this case 3. And the name is, of course, scores, which in English I've just deliberately pluralized now so that I can describe this array as storing multiple scores indeed.
It's like having
So if I want to
3
now assign values
separate,
to this
3 individual
variable
variables of the
called
same
scores,
name, right?
I can do code like this.
Like that.
I can say scores bracket 0 equals 72. Scores bracket 1 equals 73, and scores bracket 2 equals 33. The only thing weird there is admittedly the square brackets, which are still new. But we're also, notice, 0 indexing things. To 0 index means to start counting at 0. And we've talked about that before. Our for loops have generally been 0 indexed. Arrays in C are 0 indexed. And you do not have choice over that. You can't just start counting at 1 in arrays just because you prefer to. You'd be sacrificing one of the elements. You have to start in arrays counting from 0. So out of context, this doesn't necessarily solve a problem, but it definitely is going to once we have more than even 3 scores here. In fact, let me go ahead and change this program a little bit. Let me go back to VS Code here, and let me go ahead and delete these 3 lines here, and let me replace it with a scores variable that's ready to store 3 total integers. And then let me go ahead and initialize them as follows. Scores bracket 0 is 72 as before. Scores bracket 1 is going to be 73. Scores bracket 2 is going to be 33. Notice I do not need to say.
So you see that with arrays, you access the different or the individual values of it through array indexing. Okay, so with C, you start with 0 and onwards. Much the same with C#, you also access array via 0-based index. So if you're interested in how it's done in C, it's much like it's very similar. I mean, how it's done in C#, it's quite similar. I have a lesson here on the channel where it discusses arrays in C#. Okay.
Int before any of these lines, because that's been taken care of already for me on line 5, where I already specified that everything in this array is going to be an int.
Yeah.
Now down here, this code needs to change because I no longer have 3 variables, score 1, 2, and 3. I have 1 variable, but that I can index into. I'm going to here then do scores bracket 0 plus scores bracket 1 plus scores bracket 2. which is equivalent to what I did earlier, giving me back those 3 integers. But notice I'm using the same variable name every time. And again, I'm using this new square bracket notation to quote unquote index into the array to get at the first int, the second int, and the third, and then to do it again down here. Now, this program's still not really solving all the problems we described. Like, I still can only store 3 scores, but we'll come back to something like that before long. But for now, we're just introducing a new syntax and a new feature whereby I can now store multiple values in the same variable. Well, let's enhance this a bit more. Instead of hard coding these scores, as was identified as a problem, let's go ahead and use getInt to ask the user for a score. Let's then use getInt to ask the user for another score. Let's use getInt to ask the user for a third score, storing them in those respective locations. And now, if I go ahead and save this program, recompile scores, I've messed up here, but now these errors should be getting a little familiar. What mistake did I make?
No reference to the CS50
Let me give
library.
folks a moment. CS50.h. So yeah, that was not intentional. So still making mistakes all these years later. I need to include CS50.h. Now I'm going to go back to the bottom in the terminal window, make scores. OK, we're back in business, /scores. Now the program's getting a little more interesting. So maybe this year was better, and I got 100 and a 99 and a 98. And there my average is 99.0000. So now it's a little more dynamic. So it's a little more interesting, but it's still capping the number of scores at 3, admittedly. But now I've kind of introduced another sort of symptom of bad programming. There's this expression in programming too called code smell, where like something smells a little off. And there's something off here in that I could do better with this code here. Does anyone see an opportunity to improve the design of this code here? If my goal still is just to get 3 scores from the user, but without it like smelling kind of bad. Yeah.
Don't repeat yourself.
Yeah, exactly. Those lines of code are almost identical. And honestly, the only thing that's changing is the number, and it's just incrementing by 1. We have all of the building blocks to do this better. So let me go ahead and improve this. Let me go ahead and delete that code. Let me go ahead now and have a for loop. So for int I gets 0, I less than 3, I plus plus. Then inside of this for loop, I can distill all 3 of those lines into something more generic, like scores bracket I equals getInt, and now ask the user just once via getInt for a score. So this is where arrays start to get pretty powerful. You don't have to hard code, that is literally type in all of these magic numbers like 0, 1, and 2. You can start to do it programmatically as you propose with a loop. So now I've kind of tightened things up. I'm now dynamically getting 3 different scores, but putting them in 3 different locations. And so this program ultimately is going to work pretty much the same. Make scores, /scores, and 100, 99, 98,
the same.
And we're back to the same answer. But it's a little better designed too. If I really want to nitpick, there's something that still smells a little bit here. The fact that I have indeed this magic number 3 here that really kind of has to be the same as this number here. Otherwise, who knows what's going to go wrong? So what might be a solution per last week to kind of cleaning that code up further too?
Get the length of the scores array.
OK, so we could leave it up to the user's discretion. And so we could actually do something like this. Let me take this a few steps ahead. Let me say something like int n gets getInt, how many scores, question mark. Then I could actually change this to an n and then this to an end, and indeed make the whole program dynamic. Ask the human how many tests have there been this semester. Then you can type in each of those scores, because the loop is going to iterate that many times. And then you'll get the average of 1 test, 2 tests, 3. Oh, I lost another. Or however many scores that were actually specified by the user. Yeah, question? How many bytes are used in an array? So the purpose of an array is not to save space. It's to eliminate having multiple variable names, because that just gets very messy quickly if you literally have score 1, score 2, score 3, ... score 99. That's literally like 99 different variables potentially that you could actually collapse into one variable that has 99 locations, if you will, at different indices or indexes, as someone would say. The index for an array is whatever's in the square brackets. So it's a good question. So if I'm using ints for everything. And honestly, we don't really need ints for scores because I'm not really likely to get a 2 billion on a test anytime soon. And so you could actually use different data types. And that list we had on the screen earlier is not all of them. There's actually a data type called short, which is literally shorter than an int. You could actually technically use char in some form, or even other data types as well. Generally speaking, in the year 2021, these tend to be overly optimized decisions. Like everyone just uses ints, even though no one's going to get a test score that's 2 billion or more, because int is just kind of the go-to. Years ago, memory was expensive, and every one of your instincts would have been spot on because memory is so tight. But nowadays, we don't worry as much about it. Yeah? So what is the difference between dividing two ints and not getting an error, as you might have encountered in a program like cache, versus dividing two ints and getting an error like I did a moment ago? The problem with the scenario I created a moment ago was printf was involved. And I was telling printf to use a %f, but I was giving printf the result of dividing integers by another integer. So it was printf that was yelling at me. And I'm guessing in the scenario you're describing for something like cache, printf was not involved in that particular line of code. So that's the difference there. All right, so we now have this ability to create an array, and an array can store multiple values. What then might we do that's more interesting than just storing numbers in memory? Well, let's take this one step further. As opposed to just storing 72, 73, 33, or 100, 99, 98 at these given locations, because again, an array gives you one variable name, but multiple locations or indices therein, bracket 0, bracket 1, bracket 2, on up, if it were even bigger than that. Let's now start to consider something more modest, like simple chars. Chars being 1 byte each, so they're even smaller. They take up much less space. And indeed, if I wanted to say a message like hi, I could use 3 variables. If I wanted a program to print hi, hi exclamation point, literally, I could, of course, store those in 3 variables, like C1, C2, C3. And let's just, for the sake of discussion, let's go ahead and whip this up real quickly. Let me create a new program here now in VS Code. This time I'm going to call it hi.c. And I'm not going to bother with the CS50 library here. I just need the standard IO one for now. Int main void. And then inside of main, I'm going to simply create 3 variables. And this is already, hopefully, striking you as a bad idea. But we'll go down this road temporarily with C1 and C2, and finally C3, storing each character in the phrase I want to print. And I'm going to go ahead now and print this in a different way than usual. Now I'm dealing with chars, and we've generally dealt with strings, which was easier certainly last week. But %c, %c, %c will let me print out 3 chars, and like C1, C2, and C3. So kind of a stupid way of printing out a string. So we already have a solution to this problem last week. But let's just poke around at what's actually going on underneath the hood here. So let's make hi, /hi, and voila. No surprise. But we, again, could have done this last week with a string and just 1 variable, or even 0 at that. But let's go ahead now and start converting these characters to their apparent numeric equivalents like we talked about in week 02. Let me go ahead and modify these %c's just to be fun to be %i's. And let me just add some spaces so that there are gaps between each of them. Let me now recompile hi, and let me rerun it. And just to guess, what should I see on the screen now?
Numeric
Any guesses?
representation.
Yeah. The ASCII values. And it's intentional that I keep using the same word, hi, because it should be, hopefully, the old friends 72, 73, and 33, which is to say that C knows about ASCII, or equivalently Unicode, and can do this conversion for us automatically. And it seems to be doing it implicitly for us, so to speak. Notice that C1, C2, and C3 are obviously chars. But printf is able to tolerate printing them as integers. If I really wanted to be pedantic, I could use this technique, again known as typecasting, where I can actually convert one data type to another if it makes logical sense to do so. And at the end of the day, we saw in week 0, chars or characters are just numbers, like 72, 73, and 33. So I can actually use this parenthetical expression to convert, incorrectly, 3 chars to 3 integers instead. So that's what I meant to type the first time. There we go. Strike 2 today. So parenthesis int close parenthesis just says take whatever variable comes after this, C1 or C2 or C3, and convert it to an int. The effect is going to be no different here. Make high and then rerunning, whoops, then running /high still works the same. But now I'm explicitly converting chars to ints. And we can do this all day long. Chars to ints, floats to ints, ints to floats. Sometimes it's equivalent. Other times you're going to lose information. Taking a float to an int just intuitively is going to throw away everything after the decimal point, because after all, an int has no decimal point. But for now, I'm going to go ahead and rewind to the version of this that just did implicit type conversion or implicit casting, just to demonstrate that we can indeed see the values underneath the hood. All right, let me go ahead and do this now the week 1 way. This was kind of stupid. Let's just do printf, quote unquote. Actually, let's do this. String s equals quote unquote high. And then let's go ahead and do a simple printf with %s, printing out s is there. So now I've rewound to last week where we began this story. But you'll notice that if we keep playing around with this, whoops, what did I do here? Oh, and let me introduce the CS50 library here. More on that before long. Let me go ahead and recompile, rerun this. We seem to be coding in circles here. Like I've just done the same thing multiple different ways. But there's clearly an equivalence then between sequences of chars and strings. And if you do it the real pedantic way, you have like 3 different variables, C1, C2, C3, representing HI exclamation point. Or you can just treat them all together like this, HI exclamation point. But it turns out that strings are actually implemented by the computer in a pretty now familiar way. What might a string actually be?
They're
As
just
of
an
this
array,
point in
array
the
of
story.
chars.
Where are we going with this? Let me
Sequence
try to
of
look farther
chars.
back. Yeah, and way back? Yeah. Yeah, a string might be, and indeed is, just an array of characters. So last week we just took for granted that strings exist. Technically, strings exist, but they're implemented as arrays of characters, which actually opens up some interesting possibilities for us. Because let me see if I can do this. Let me try to print out now 3 integers again. But if string s is but an array, as you propose, maybe I can do s bracket 0, s bracket 1, and s bracket 2. So maybe I can start poking around inside of strings, even though we didn't do this last week, so I can get at those individual values. So make high, /high, and voila, there we go again. It's the same 72, 73, 33, but now I'm sort of hopefully like wrapping my mind around the fact that, all right, a string is just an array of characters, and arrays you can index into them using this new square bracket notation. So I can get at any one of these individual characters and heck, convert it to an integer like we did in week 0, as I might. But let me get a little curious now too. What else might be in the computer's memory? Well, let's toggle back to the depiction of these same things. Here might be how we originally implemented high with 3 variables, C1, C2, C3. Of course, that mapped to these decimal digits or equivalent these binary values. But what was this looking like in memory? Literally, when you create a string in memory like this, string s equals quote unquote high, let's consider what's going on underneath the hood, so to speak. Well, as an abstraction, a string, it's HI exclamation point taking up, it would seem, 3 bytes, right? I've gotten rid of the bars there because if you think of a string as a type, I'm just going to use one big box of size 3. But technically, a string we've just revealed is an array, and the array is of size 3. So technically, if the string is called s, s bracket 0 will give you the first character, s bracket 1 the second, and s bracket 3 the third. But let me ask this question now. If this, at the end of the day, is the only thing in your computer, memory, and the ability, like a canvas, to draw zeros and ones or numbers or characters or whatever on it, but that's it. Like this is what your Mac and PC and phone ultimately reduce to. Suppose that I'm running a piece of software, like a text messenger, and now I write down by exclamation point. Well, where might that go in memory? Well, it might go here, B-Y-E. And then the next thing I type might go here, 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 and so forth. My memory just might get filled up over time with things that you or someone else are typing. But then how does the computer know if potentially B-Y-E exclamation point is right after H-I exclamation point, where one string ends and the next one begins? Right? All we have are bytes or zeros and ones. So if you were designing this, how would you implement some kind of delimiter between the two or figure out what the length of a string is? What do you think? OK, so the right answer is use a null character. And for those who don't know, what does that mean?
Empty. Sort of like a space.
Yeah, so it's a special character. Let me describe it as a sentinel character. Humans decided some time ago that, you know what, if we want to delineate where one string ends and where the next one begins, we just need some
Sorry about that. Yeah. Let's continue.
special symbol. And the symbol they'll use is generally written as \0. This is just shorthand notation for literally 8 0 bits. 0, 0, 0, 0, 0, 0, 0, 0. And the nickname for 8 0 bits in this context is null, N-U-L, so to speak. And we can actually see this as follows. If you look at the corresponding decimal digits, like you could do by just doing out the math or doing the conversion like we've done in code, you would see for storing high, 72, 73, 33, but then one extra byte that's sort of invisibly there, but that is all zeros. And now I've just written it as the decimal number 0. The implication of this is that the computer is apparently using not 3 bytes to store a word like high, but 4 bytes. Whatever the length of the string is, plus 1 for this special sentinel value that demarcates the end of the string. So we might draw it like this instead. And this character is, again, sort of pronounced null, or written N-U-L. So that's all, right? If humans at the end of the day just have this canvas of memory, they just needed to decide, all right, well, how do we distinguish one string from another? Because it's a lot easier with chars individually. It's a lot easier with ints. It's even easier with floats. Why? Because per that chart earlier, every character is always 1 byte. Every int is always 4 bytes. Every long is always 8 bytes. How long is a string? Well, hi is 1, 2, 3 with an exclamation point. Bye is 1, 2, 3, 4 with an exclamation point. David is D-A-V-I-D 5 without an exclamation point. And so a string can be any number of bytes long. So you somehow need to draw a line in the sand to separate in memory one string from another. So what's the implication of this? Well, let me go back to code here. Let's actually poke around. This is a bit dangerous, but I'm going to start looking at memory locations past my string here.
Out of range.
So let me go ahead and recompile make hi. Whoops. What did I do here? Oh, I forgot a format code. Let me add one more %i. Now let me go ahead and rerun make hi, /hi, enter. There it is. So you can actually see in the computer, unbeknownst to you previously, that there's indeed something else going on there. And if I were to make like one other variant of this program, let's get rid of just this one word, and maybe let's have two. So let me give myself another string called t, for instance, just as is common convention, with by exclamation point. Let me then go ahead and print out with %s, s, and let me also print out with %s, whoops, printf, print out t as well. Let me just recompile this program. And obviously, the out. Oh, this is what happens when I go too fast. All right, third mistake today. Close quote, as I was missing, make hi. Fourth mistake today, make hi, /hi. OK, voila. Now we have a program that's printing both hi and bye, only so that we can consider what's going on in the computer's memory. If s is storing hi, and apparently one bonus byte that demarcates the end of that string, bye is apparently going to fit into the location directly after. And it's wrapping around, but that's just an artist's rendition here. But bye, B-Y-E exclamation point, is taking up 1, 2, 3, 4, plus a 5th byte as well. Whew. All right, any questions on this underlying representation of strings? And we'll contextualize this before long so that this isn't just like, OK, who really cares? This is going to be the source of actually implementing things, in fact, for problem set 2, like cryptography and encryption and actually scrambling actual human messages. But some questions first.
So if normally if you were to like not use string, you would just make a character array, you have to declare how many characters there are, or you know how many characters are going to be there.
A good question, too. And let me summarize as if we were instead to use chars all the time, we would indeed have to know in advance how many chars you want for a given string that you're storing. How then does something like getString work? Because when CS50 wrote the getString function, we obviously don't know how long the words are going to be that you all are typing in. It turns out next 2 weeks from now, we'll see that getString uses a technique known as dynamic memory allocation, and it's going to grow or shrink the array automatically for you. But more on that soon. Other questions? Good question. Why are we using a null value? Isn't it wasting a byte? Yes, but I claim there's really no other way to distinguish the end of one string from the start of another unless we make some sort of notation, so to speak, in memory. All we have at the end of the day inside of a computer are bits. Therefore, all we can do is spend those bits in some creative way to solve this problem. And so we're minimally going to spend 1 byte to solve this problem here. Yeah? If you don't, how does the computer know to move to a next line when you have a \n? So \n, even though it looks like 2 characters, it's actually stored as just 1 byte in the computer's memory. There's a mapping between it and an actual number. And you can see that, for instance, on the ASCII chart from the other day. It would be. If I had put a \n in my code here, right after the exclamation point here and here, that would actually shift everything in memory because we would need to make room for a \n here and another one over here. So it would take 2 more bytes. Exactly. Other questions?
So if I exclamation point is written in binary and ASCII too, as 72, 73, 33, if we were to write those numbers in a string and convert them into binary, how would the computer know what's 72 and what's 8?
And what's the last thing you said?
8, for example.
It's context sensitive. So if at the end of the day, all we're storing is these numbers like 72, 73, 33, recall that it's up to the program to decide based on context how to interpret them. And I simplified this story in week 0, saying that Photoshop interprets them as RGB colors, and iMessage, or a text messaging program, interprets them as letters, and Excel interprets them as numbers. How those programs do it is by way of variables like string and int and float. And in fact, later this semester, we'll see a data type via which you can represent a color as a triple of numbers, and red value, a green value, and a blue value. So we'll see other data types as well. Yeah?
Yeah, it seems easy enough to just add a null thing at the end of a word. So why do we have integers and long integers? Why can't we make everything variable in its data size?
Really interesting question. Why could we not just make all data types variable in size? And some languages, some libraries do exactly this. C is an older language, and so because memory was expensive, memory was limited, the reality was you gain benefits from just standardizing the size of these things. You also get performance increases in the sense that if you know every int is 4 bytes, you can very quickly, and we'll see this next week, jump from integer to another in memory just by adding 4 inside of those square brackets. You can very quickly poke around. Whereas if you had variable length numbers, you would have to kind of follow, looking for the end of it. Follow. You would have to look at more locations in memory.
If you have variable length of values and variables, I guess you would quickly consume so much memory, which is not optimal, because you have to accommodate all of possible sizes.
So that's a topic we'll come back to. But it was generally for efficiency. And other question, yeah?
Why not store the null character at like position 0 and start the indexing from 1?
Good question. Why not store the OK, same one. Why not store the null character at the beginning? You could, let's see, why not store it at the beginning? You could do that. You could absolutely, well, could you do this?
It would depend.
If you were to do that at the beginning, short answer, no. OK, I retract that. No, because I finally thought of a problem with this. If you store it at the beginning instead, we'll see in just a moment how you can actually write code to figure out where the end of a string is. And the problem there is you wouldn't necessarily know if you eventually hit a 0 at the end of the string because it's the number 0 in the context of like Excel using some memory, or if it's the context of some other data type altogether. So the fact that we've standardized, strings as ending with null means that we can reliably distinguish one variable from another in memory. And that's actually a perfect segue now to actually using this primitive to building up our own code that manipulates these things at a lower level. So let me go ahead and do this. Let me create a new file this time called length. And let's just use this basic idea to figure out what the length of a string is after it's been stored in a variable here. So let's go ahead and do this. Let me include both the CS50 header and the standard IO header. Give myself int main void again here. And inside of main, let me go ahead and do this. Let me prompt the user for a string s. And I'll ask them for a string like their name here. And then let me go ahead and actually, let me name it more verbosely name this time. And now let me go ahead and do this. Let me iterate over every character in this string in order to figure out what its length is. So initially, I'm going to go ahead and say this. Int length equals 0, because I don't know what it is yet. So we're going to start at 0. And then while the following is true, while, do I want to do this? Let me change this to I, just for clarity. Let me go ahead and do this. While name bracket I does not equal that special null character. So I typed it on the slide as NUL, but you don't write NUL in code. You actually use its numeric equivalent, which is +0 in single quotes. While name bracket I does not equal the null character, I'm going to go ahead and increment I to I++. And then down here, I'm going to print out the value of I to see what we actually get. Printing out the value of I. All right, so what's going to happen here? Let me go ahead and run make length. Fortunately, no errors. /length. And let me type in something like hi exclamation point enter. And I get 3. Let me try by exclamation point, enter. And I get 4. Let me try my own name, David, enter. 5, and so forth. So what's actually going on here? Well, it seems that by way of this for loop, we are specifying a local variable called I, initialized to 0, because we're figuring out the length of the string as we go. I'm then asking the question, does location 0, that is I, in the name string, which we now know is an array, does it not equal \0? Because if it doesn't, that means it's an actual character like H or B or D. So let's increment I. Then let's come back around to line 9 and let's ask the question again. Now I equals 1. So does name bracket 1 not equal \0? Well, if it doesn't, and it won't if it's an I or a Y or an A based on what I typed in, we're going to increment I once more. Fast forward to the end of the story. Once I get to the end of the string, technically one space past the end of the string, name bracket I will equal \0. So I don't increment I anymore. I end up just printing the result. So what we seem to have here with some low-level C code, just this while loop, is a program that figures out the length of a given string that's been typed in. Let's practice our abstraction and decompose this into maybe a helper function here. Let me actually grab all of this code here. And let me assume for the sake of discussion for a moment that I could just call a function now called string length. And the length of the string is name that I want to get. And then I'll go ahead and print out, just as before, with %i, the length of that string. So now I'm abstracting away this notion of figuring out the length of a string. That's an opportunity for me to create my own function. If I want to create a function called string length, I'll claim that I want to take a string as input. And what should I have this function return as its return type? What should getString presumably return? Yeah. An int, right? An int makes sense. Float really wouldn't make sense because we're measuring things that are integers, in this case, the length of something. So indeed, let's have it return an int. I can pretty much use the same code as before. So I'm just going to paste what I cut earlier in the file. And the only thing I have to change here is the name of the variable. Because now this function, I decided kind of arbitrarily that I'm going to call it s, just to be more generic. So I'm going to look at s bracket I at each location. And I don't want to print it at the end. This would be a side effect. What's the line of code I should include here if I actually want to hand back the total length? Yeah. Say again? Return I in this case. So I'm going to go ahead and return I, not print it, because now my main function can use the return value stored in length and print it on the next line itself. I just need a prototype. So that's my one forgivable copy paste here. I'm going to rerun make length. Hopefully I didn't screw up. I didn't. /length. I'll type in hi. Whoops. I'll type in hi again. That works. I'll type in by again, and so forth. All right. So now we have a function that determines the length of a string. Well, it turns out we didn't actually need this all along. It turns out that we can get rid of my own custom string length function here. I can definitely delete the whole implementation down here, because it turns out in a file called string.h, which is a new header file today, we actually have access to a function called, more succinctly, strlen, S-T-R-L-E-N, which literally does that. This is a function that comes with C, albeit in the string.h header file, and it does pretty much what we just implemented manually. So here's an example of, admittedly, a wheel we just reinvented, but no more. We don't have to do that. And how do you know what kinds of functions exist? Well, let me actually pop out of my browser here to a website that is a CS50's incarnation of what are called manual pages. It turns out that on a lot of systems, Macs and Unix and Linux systems, including the Visual Studio Code instance that we have in the cloud, there are publicly accessible manual pages for functions. They tend to be written very expertly in a way that's not very beginner friendly. So what we have here at manual.cs50.io is CS50's version of manual pages that have this less comfortable mode that give you a sort of cheat sheet of very frequently used helpful functions in C. And we've translated the sort of expert notation to things that a beginner can understand. So for instance, let me go ahead and search for string up at the top here. You'll see that there's documentation for our own getString function. But more interestingly, down here, there's a whole bunch of string-related functions that we haven't even seen most of yet. But there's indeed one here called strlen, calculate the length of a string. And so if I actually go to strlen here, I'll see some less comfortable documentation for this function. And the way a manual page typically works, whether in CS50's format or any other system, is you see typically a synopsis of what header files you need to use the function. So you would copy paste these couple of lines here. You see what the prototype is of the function so that you know what its inputs are, if any, and its outputs are, if any. Then down below you might see a description, which in this case is pretty straightforward. This function calculates the length of s. Then you see what the return value is, if any, and you might even see an example like this one that we've whipped up here. So these manual pages, which are, again, accessible here, and we'll link to these in the problem sets moving forward, are pretty much the place to start when you want to figure out, has a wheel been invented already? Is there a function that might help me solve some problem set problem so that I don't have to really get into the weeds of doing all of those lower level steps as I've had? Sometimes the answer is going to be yes, sometimes it's going to be no. But again, the point of our having just done this together is to reveal that even the functions you start taking for granted, they all reduce to some of these basic building blocks. At the end of the day, this is all that's inside of your computer, is zeros and ones. We're just learning now how to harness those and how to manipulate them ourselves. All right, any questions here on this? Any questions at all? Yeah. Good question. Is it so common that you would have to specify it or not? You do need to include its header files, because that's where all of those prototypes are. You don't need to worry about linking it in with -l anything. And in fact, moving forward, you do not ever need to worry about linking in libraries when compiling your code. We, the staff, have configured Make to do all of that for you automatically. We want you to understand that it is doing it, but we'll take care of all of the -ls for you. But the onus is on you for the prototypes and the header files. Other questions on these representations or techniques? Yeah? A good question. If you were to have a string with actual spaces in it, that is multiple words, what would the computer actually do? Well, for this, let me go to ASCIIchart.com, which is just a random website that's my go-to for the first 127 characters of ASCII. This is, in fact, what we had a screenshot of the other day. And if you look here, it's a little non-obvious, but SP is space. If a computer were to store a space, it would actually store the decimal number 32, or technically the pattern of zeros and ones that represent the number 32. All of the US English keys that you might type on a keyboard can be represented with a number. And using Unicode, can you express even things like emojis and other languages? Yeah?
Are only strings followed by a null number, or let's say we had a series of numbers, would each one of them be accompanied by null?
Good question. Only strings are accompanied by nulls at the end, because every other data type we've talked about thus far is of well-defined finite length. 1 byte for char, 4 bytes for ints, and so forth. If we think back, though, to last week, we did end the week with a couple of problems. Integer overflow, because like 4 bytes, heck, even 8 bytes is sometimes not enough. We also talked about floating point imprecision. Thankfully, in the world of scientific computing and financial computing, there are libraries you can use that draw inspiration from this idea of a string. And they might use 9 bytes for an integer value, or maybe 20 bytes. You can count really high, but they will then start to manage that memory for you. And what they're really probably doing is just grabbing a whole bunch of bytes and somehow remembering how long the sequence of bytes is. That's how these higher level libraries work too. All right, this has been a lot. Let's take one more break here. We'll do like a 7-minute break here. And when we come back, we'll flesh out a few more details. All right. So we just saw strlen as an example of a function that comes in the string library. Let's start to take more of these library functions out for a spin, so we're not relying only on the built-ins that we saw last week. Let me go ahead and switch over to VS Code, and let me create a file called, say, string.h, just to kind of apply this lesson learned as follows. Let me go ahead and include CS50.h. Let me include standard.io.h, and this new thing, string.h as well at the top. I'm going to do the usual int main void here. And then in this program, suppose for the sake of discussion that I didn't know about %s for printf, or heck, maybe early on there was no %s format code. And so there was no easy way to print strings. Well, at least if we know that strings are just arrays of characters, we could use %c as a workaround, so to speak, a solution to that sort of contrived problem. So let me ask myself for a string s by using getString here, and I'll ask the user for some input. And then let me go ahead and print out, say, output. And all I want to do is print back out what the user typed. Now, the simplest way to do this, of course, is going to be like last week, printf %s, and plug in the s, and we're done. But again, for the sake of discussion, I forgot about, or someone didn't implement %s. So how else could we do this? Well, in pseudocode or in English, like what's the gist of how we could solve this problem? Printing out the string s on the screen without using %s. How might we go about solving this? Just in English, high level. What would your pseudocode look like? Yeah? OK, so just print each letter, and maybe more precisely, like some kind of loop. Like let's iterate over all of the characters in s and print one at a time. So how can I do that? Well, for int I gets 0 is kind of the go-to starting point for most loops. I is less than, OK, how long do I want to iterate? Well, it's going to depend on what I type in, but that's why we have strlen now. So iterate up to the length of s, and then increment I with ++ on each iteration. And then let's just print out %c with no new line, because I want everything on the same line, whatever the character is at s bracket I. And then at the very end, I'll give myself that new line just to move the cursor down to the next line so the $sign's not in a weird place. All right, so let's see. If I didn't screw up any of the code, make string, enter. So far, so good. String, and let me type in something like hi, enter. And I see output of hi 2. Let me do it once more with by, enter. And that
Jolly Savers, bestseller sa sarap at sulit. Starts at 40 pesos.
And that works too. Notice I very deliberately and quickly gave myself 2 spaces here and 1 space here just because I literally wanted these things to line up properly, and input is shorter than output. But that was just a deliberate formatting detail. So this code is correct, which is a claim I've made before, but it's not well designed. Now, it is well designed in that I'm using someone else's library function. Like I've not reinvented a wheel. There's no line 15 or below. I didn't implement string length myself. So I'm at least kind of practicing what I've preached. But there's still an imperfection, a suboptimality. This one's really subtle, though. And you have to think about how loops work. What am I doing that's not super efficient? Yeah, and back?
Strlen.
Yeah, this is a little subtle, but if you think back to the basic definition of a for loop, and recall when I highlighted things last week, what happens?
So
well, the first thing is that I gets set to 0. Then we check the condition. How do we check the condition? We call strlen on s. We get back an answer like 3 if it's hi exclamation point. And 0 is less than 3, so that's fine. And then we print out the character. Then we increment I from 0 to 1. We recheck the condition. How do I recheck the condition? I call strlen of s, get back the same answer, 3, compare 3 against 1. We're still good, so we print out another character. I gets incremented again. I is now 2. We check the condition. What's the condition? Well, what's the string length of s? It's still 3. 2 is still less than 3. So I keep asking the same question sort of stupidly because the string is presumably never changing in length. And indeed, every time I check that condition, that function is going to get called. And every time the answer for hi is going to be 3, 3, 3. So it's a marginal sort of suboptimality, but I could do better, right? Like don't ask multiple times questions that you can remember the answer to. So how could I remember the answer to this question and ask it just once?
Put it in a separate
How could I
variable
remember
outside, or
the answer to this question? Let me see. Yeah, back there? So stored in a variable, right? That's been our answer most any time we want to keep something around. So how could I do this? Well, I could do something like this. Int maybe length equals strlen of s. Then I can just change this function call, so to speak. And let me refix my spelling here. Let me fix this to be now comparing against length. And this is now OK, because now Sterling is only called once on line 9, and I'm reusing the value of that variable, aka length, again and again and again, so that's more efficient. Turns out that for loops actually let you declare multiple variables at once, so we can actually do this a little more elegantly, all in one line. And this is just now some syntactic improvement. I could actually do something like this. N equals Sterling of S. And then I could just say n here. Or I could call it length. But heck, while I'm being succinct, I'm just going to use n for number. So now it's just a marginal change. But I've now declared two variables inside of my loop, I and n. I is set to 0. N is set to the string length of s. But now, hereafter, all of my condition checks are just I less than n, and n is never now changing. All right, so a marginal improvement there. Now that I've used this new function, let's use some other functions that might be of interest. Let me go ahead and write a quick program here that maybe like capitalizes the beginning of, changes to uppercase some string that the user types in. So let me go ahead and code a file called uppercase.c. Up here, I'll use my new friends, CS50.h and standard.io and string.h. So standard.io and string.h. So just as before, int main void. And then inside of main, what I'm going to do this time is, well, let's ask the user for a string s using getString, asking them for the before value. And then let me go ahead and just print out something like after, so that it, just so I can see what the uppercase version thereof is. And then after this, let me go ahead and do the following. For int I equals 0. Oh, let's practice that same lesson. So n equals the string length of s. I is less than n, I plus plus. So really nothing new, really, fundamentally yet. How do I now convert characters from lowercase, if they are, to uppercase? In other words, if I type in hi, hi in lowercase, I want my program now to uppercase everything to capital H, capital I. Well, how can I go about doing this? Well, you might recall that there is this ASCII chart. So let's just consult this real quick. On the ASCIIchart.com, we've looked at this last week. Notice that A, capital A, is 65, capital B is 66, capital C is 67, and heck, here's lowercase a, lowercase b, lowercase c, and that's 97, 98, 99. And if I actually do some math, there's like a distance of 32. Right? So if I want to go from uppercase to lowercase, I can do 65 plus 32 will give me 97. And that actually works out across the board for everything else. 66 plus 32 gets me to 98 or lowercase b. Or conversely, if you have a lowercase a and its value is 97, subtract 32 and boom, you have capital A. So, all right, there's some arithmetic here involved. But now that we know that strings are just arrays and we know that characters, which are in those arrays, are just binary representations of numbers, I think we can manipulate a few of these things as follows. Let me go back to my program here and first ask the question, if the current character in the array during this loop is lowercase, let's force it to uppercase. So how am I going to do that? If the character at s bracket I, the current location in the array, is greater than or equal to lowercase a and s bracket I is less than or equal to lowercase z. Kind of a weird Boolean expression, but completely legitimate.
Just comparing numbers
because
still.
In this array s is a whole bunch of characters that the humans typed in, because that's what a string is. Greater than or equal to a might be a little nonsensical, because when have you ever compared numbers to letters? But we know from week 0, lowercase a is 97. Lowercase z is, what is it, 1? I don't even remember.
So you have to remember, if you're dealing with individual characters or chars, or char, it is in single quotes. If you're dealing with strings, it is in double quotes. OK?
Why is that? 132, we know. And so that would allow us to answer the question, is the current letter lowercase? All right, so let me go ahead here and answer that question. If it is, what do I want to print out? I don't want to print out the letter itself. I want to print out the letter minus 32, right? Because if it happens to be a lowercase a, 97, 97 minus 32 gives me 65, which is uppercase a. And I know that just from having stared at that chart in the past. Else, if the character is not between little a and big A, I'm just going to print out the character itself by printing s bracket I. And at the very end of this, I'm going to go ahead and print out a new line just to move the cursor to the next line. So again, it's a little wordy, but this loop here, which I borrowed from our code previously, just iterates over the string, aka array, character by character through its length. This line 11 here is just asking the question if that current character, the ith character of s, is greater than or equal to little a and less than or equal to little z, that is between 97 and 132, then we're going to go ahead and force it to uppercase instead. All right, and let me go ahead and zoom out here for just a second. And sorry, I misspoke. 122, which is what you might have said. There's only 26 letters. So 122 is little z. Let me go ahead now and compile and run this program. So make uppercase, / uppercase, and let me type in high and lowercase, enter, and there's the capitalized version thereof. Let me do it again with like my own name in lowercase. And now it's capitalized as well. Well, what could we do to improve this? Well, you know what? Let's stop reinventing wheels. Let's go to the manual pages. So let me go here and search for something like, I don't know, lowercase. And there I go. I did some autocomplete here. Our little search box is saying that, OK, there's an is lower function. Check whether a character is lowercase. Well, how do I use this? Well, let me check is lower. Now I see the actual man page for this function. Now we see include ctype.h. So that's the header file I need to include. This is the prototype for is lower. It apparently takes a char as input and returns an int, which is a little weird. I feel like is lower should return true or false. So let's scroll down to the description and return value. It returns, oh, this is interesting, and this is a convention in C. This function returns a non-zero int if C is a lowercase letter, and 0 if C is not a lowercase letter. So it returns non-zero. So like 1, -1, something that's not 0 if C is a lowercase letter, and 0 if it is not a lowercase letter. So how can we use this building block? Let me go back to my code here. Let me add this file, include ctype.h. And down here, let me get rid of this cryptic expression, which was kind of painful to come up with, and just ask this, is lower s bracket I? That should actually work. But why?
Greater than.
Well, is lower, again, returns a non-zero value if the letter is lowercase. Well, what does that mean? That means it could return 1, it could return -1, it could return 50 or -50. It's actually not precisely defined. Why? Just because. Like this was a common convention to use 0 to represent false and use any other value to represent true. And so it turns out that inside of Boolean expressions, if you put a value, like a function call like this, that returns 0, that's going to be equivalent to false.
Yeah.
It's like the answer being no, it is not lower. But you can also just in parentheses put the name of the function and its argument and not compare it against anything, because we could do something like this. Well, if it's not equal to 0, then it must be lowercase, because that's the definition. If it returns a non-zero value, it's lowercase. But a more succinct way to do that is just a bit more like English. If it is lower, then print out the character -32. So this would be the common way of using one of these is functions to check if the answer is true or false. OK, well, we might be done. OK. No, so it's not necessarily 1. It would be incorrect to check for 1 or -1 or anything else. You want to check for the opposite of 0, so not equals 0, or more succinctly, like I did by just putting it into parentheses. Let me see what happens here. So this is great, but some of you might have spotted a better solution to this problem a moment ago when we were on the manual pages searching for things related to lowercase. What might be another building block we can employ here? Based on what's on the screen here. Yeah. So to upper, there's a function that would literally do the uppercasing for me, so I don't have to get into the weeds of like -32 plus 32. I don't have to consult that chart. Someone has solved this problem for me in the past. And let's see if I can actually get back to it. There we go. Let me go ahead now and use this. So instead of doing s bracket I minus 32, let's use a function that someone else wrote and just say 2 upper s bracket I. And now it's going to do the solution for me. So if I rerun make uppercase and then do slowly dot uppercase, type in hi, now it's working as expected. And honestly, if I read the documentation for 2 upper by actually going back to its man page or manual page, what you'll see is that it says if it's lowercase, it will return the uppercase version thereof. If it's not lowercase, it's already uppercase, it's punctuation, it will just return the original character, which means thanks to this function, I can actually tighten this up significantly, get rid of all of my conditional there, and just print out the 2 upper return value and leave it to whoever wrote that function to figure out if something's uppercase or lowercase. All right. Questions on these kinds of tricks? Again, it all reduces to like week 0 basics, but we're just building these abstractions on top. Yeah? Yes, unfortunately, no. There is no easy way in C to say, give me everything. That was for historically performance reasons. They want you to be explicit as to what you want to include. In other languages like Python, Java, one of which we'll see later this term, you can say, give me everything. But that actually tends to be best practice because it can actually slow down execution or compilation of your code. Yeah? Does 2 upper accommodate special characters like punctuation? Yes. If I read the documentation more pedantically, we would see exactly that. It will properly hand me back an exclamation point, even if I passed it in. So if I do make uppercase here, and let me do dot slash uppercase, hi with an exclamation point, it's going to handle that too, and just pass it through unchanged. Yeah? Really good question, too. No, we do not have access to a function that at least comes with C or comes with CS50's library that will just force the whole thing to uppercase. In C, that's actually easier said than done. In Python, it's trivial. So stay tuned for another language that will let us do exactly that. All right, so what does this leave us with? There's just let's come full circle now to where we began today, where we were talking about those command line arguments. Recall that we talked about rm taking a command line argument, the file you want to delete. We talked about clang taking command line arguments that, again, modify the behavior of the program. How is it that maybe you and I can start to write programs that actually take command line arguments? Well, here is where I can finally explain why we've been typing int main void for the past week and just asking that you take on faith that it's just the way you do things. Well, by default in C, at least the most recent versions thereof, there's only 2 official ways to write main functions. You might see other formats online, but they're generally not consistent with the current specification. This, again, was sort of the boilerplate for the simplest function we might write last week. And recall that we've been doing this the whole time, void. What that void means for all of the programs I have written thus far and you have written thus far is that none of our programs that we've written take command line arguments. That's what the void there means. It turns out that main is the way you can specify that your program does, in fact, take command line arguments. That is, words after the command in your terminal window. If you want to actually not use getInt or getString, you want the human to be able to say something like, hello, David, and hit Enter, and just print hello, David on the screen. You can use command line arguments, words after the program name on your command line. So we're going to change this in a moment to be something more verbose, but something that's now a bit more familiar syntactically. If you change that void in main to be this incantation instead, int argc, comma, string argv, open bracket, close bracket, you are now giving yourself access to writing programs that take command line arguments. Argc, which stands for argument count, is going to be an integer that stores how many words the human typed at the prompt. The C automatically gives that to you. String argv stands for argument vector. That's going to be an array of all of the words that the human typed at the prompt. So with today's building block of an array, we have the ability now to let the humans type as many words or as few words as they want at the prompt. C is going to automatically put them in an array called argv. And it's going to tell us how many words there are in an int called argc.